Well, we're still in section 1.1. Now, here's a quick application that they mention. Now, they do it as example 1.13. Well, I'm not going to quite do example 1.13, so we'll call it 1.13 prime. I just don't want to deal here with as many things. So in this case, let's find a polynomial. We'll just look for a third degree polynomial. A0 plus A1x, second degree polynomial, just three variables. Let's find a polynomial of this form. Oh, cube, silly me, squared. Having a little trouble here. Okay, so a quadratic, and we need to come up with these three coefficients, A1, or A0, A1, and A2. And suppose, okay, that goes through or contains the points. Let's go with 0, 0. And let's see, and 1, 3, and then finally maybe the point 2 and 10, I think. Kind of doing this on the fly, but we'll try that. Now, if this is a polynomial, then it must be true that if I plug in 0, I need to get out 0. And so, you know, A0 plus A1 times 0 plus A2 times 0 squared has to be equal to 0. And then A0 plus A1 times 1 plus A2 times 1 squared has to be 3. And A0 plus A1 times 2 plus A2 times 2 squared has to be 10. So this is our application, is that you give me some points, I could try to fit a polynomial to them, interpolation. And now I'll rewrite this. Notice these aren't x's anymore, they're a's, because, well, we were thinking about those a's as what we don't know. The x's are just dummy variables in there that we plug in, you know, 0 and so forth. So this is one thing in the linear algebra, and in particular when you're doing applications with it, is the x's might actually be known values, as in our case 0, 1, and 2, and something else may be the actual variable you're trying to work with in the linear algebra setting. So now I can rewrite this a little bit. I've got A0 plus 0A1. Okay, so, well, there's nothing there, so I won't write anything. And then 0A2, and then equals 0. And then A0 plus A1 plus A2 has to be 3. And then A0 plus 2A1 plus 4A2 has to equal 10. So here are my three equations that I have, and three unknowns. And, well, what's really nice, and I made it that way, is that my first variable, A0, is pretty obvious what its value is. We have A0 equals 0, which now means that I can rewrite these other two equations as A1 plus A2 equals 3, and 2A1 plus 4A2 equals 10. And now, here again, what I could do is I could multiply this equation, I guess this is our equation 2, and here's equation 3, and then that a0 equals 0 is equation 1. I could take 2 times equation 2 and subtract from it, or do it the other way around, but I'm just going to do it this way, subtract equation 3. Okay, so 2 times equation 2 is 2a1 plus 2a2 equals 6. There's my 2 times equation 2, and then minus all of this equation 3, so that's 2a1 plus 4a2 equals 10. So now when I do that, those two give me 0. And then I have 2a2 minus 4a2, that's a negative 2a2. And 6 minus 10 is negative 4. So this says a2 equals 2. So now I know that a2 equals 2. And if I go up there, I have then that a1 plus 2 is equal to 3. And so a1 equals 1. And now my solution is unique. And it says that a0 equals 0, a1 equals 1, and a2 equals 2. And now I should go a little further because it asks for the polynomial. And so my polynomial is x plus 2x squared, or I could write that as y equals x plus 2x squared. And there is my solution. So there's a nice application. Again, we see that it becomes the system of equations, and we can solve that system of equations, and in this case we ended up with a unique solution.